So what we're going to talk about today is our implementation of diffraction multifocusing stacking, and this uses an image processing technique called the watershed transform to help resolve diffractions in the data space. Diffraction multifocusing is a technique that was developed by Alex Berkovich and several co-authors beginning around 1993 or so. There have been quite a few publications on the topic since then, mostly in trade journals, but for the purposes of this talk, the most important one is this one from Geophysics, which came out in 2009. It's illustrative to start with a quick rundown of normal move-out, just to contrast it with diffraction move-out. In NMO, we want to enhance reflections. We assume we've got flat layers, and we arrange traces into common midpoint gathers so that we can assume that everything we see in each gather has bounced off of something directly below the bin center. Now when we move to diffraction move-out, here we want to flatten the diffractions instead. There are a couple of big changes. For one thing, diffraction amplitudes drop off a lot faster with distance than reflection amplitudes, and also diffraction energy propagates outwards in all directions from the diffractor, so the common midpoint restriction doesn't really make sense here. It's a better idea instead to build the gathers by including all of the traces whose shot and receiver positions both lie within some threshold radius of the bin center. So I've been calling these circle gathers for that reason. This leads to very large folds of several thousand traces, but you need this to enhance the small diffraction amplitudes and to knock down the big reflections destructively. This point about knocking down reflections is one that we'll come back to later on. Another difference is that at any particular bin position, we're going to want to pick up all of the diffractors in the area, not just the ones that happen to lie straight down below the bin center. We want to pick up the ones that have lateral displacement as well so that we can build up their hyperbolas. Now, what this means for move-out correction is that the zero offset ray path to which we're correcting the travel times of the original ray path is going to have a finite tilt with an associated azimuth so that it can point towards laterally displaced diffractors. Because of this, the move-out formula ends up being a double square root equation that kind of looks like a cross between normal move-out and migration. Just a couple of technical points. If you're going to do move-out correction, you're going to need a velocity field. The velocity field that we use is the one that's obtained from conventional processing. If you're going to do that, though, you've got to remember to time dilate the velocity functions, because when you tilt the zero offset ray path like this, the energy is going to spend more time in each layer, right? Another thing is that this type of move-out makes stretch muting real fun, so if you're going to code this up, you'd better know that. Now, just to show you an example of what the move-out corrections look like, here's part of a circle gather, and this is what it looks like after move-out correction. So we'll flip back and forth a few times. You can see that it's different from normal move-out. Some things are moving up, some things are moving down. That's what you get when the shot and receiver can both be on the same side of the bin center. And this is after muting. Before, after, not a lot to discuss there except that it's a pain to code up. So this is the result that you would actually stack. Now some of you are probably already thinking, well, wait a minute, how do we know those tilt and azimuth angles? Well, we don't. So to spot the diffractors, we're going to need to run this move-out correction for many zero offset paths at each bin. This is a depiction of what those paths look like. They form a geodesic grid in tilt-azimuth space. If a zero offset path happens to pass through a diffractor, then its signature ought to show up nicely on the corresponding stack trace. That's why I got to calling these things search paths. Now, doing this changes the nature of the data volume in a big way. In NMO, stacking gives us one trace per bin, but here we get a whole ensemble of stack traces at each bin, one for each search path. So now the stack is going to have 5 dimensions. We've got the usual line, bin, and time dimensions, plus the tilt and azimuth of the search path. Well, 5-dimensional data isn't much use for interpretation. At some point, we're going to have to lose a couple of those dimensions. There are probably several ways you could do that, but the methodology we'll use will be to look at the ensemble of stacked traces at each bin and try to find some way of retaining only the diffraction signatures, zero out everything else, and then combine together whatever's left into one single stacked trace. Before we can do that, though, we need to be able to identify and delineate the diffractions. Well, clearly we're not going to be able to do this manually. That'd be hard enough to do in 3 dimensions, and in 5D it'll be impossible. We're going to need automated detection, and of course the way to do that is to use coherency. We calculate a semblance trace to go along with each stack trace, and that gives us a 5-dimensional semblance volume as well. That's where we're going to find our diffractions. They should correspond to local semblance peaks in the 5D data space, and that's how we'll determine what to keep and what to throw out. Now, there are some computational challenges that come with this. It turns out that the search grid can't have a spacing of more than a degree or two if you want to accurately resolve the semblance peaks. At least that's what we found. And also, the maximum tilt angle can't be too small, or else you'll only see the tops of the hyperbolas. You've got to go out at least 40–45 degrees, and that's with 1 to 2 degree spacing. So this means that you end up having to perform the move-out correction for a few thousand search paths at each bin. And when you consider that the circle gathers have a few thousand traces each, well, this starts to get time-consuming, much more time-consuming than normal move-out correction. It can really give your computer a workout. To visualize 5D semblance on a 2D screen, we need to look at slices through the data. I came up with this viewer to do that. The middle plot, the one with the amplitude scale, is a semblance trace, and the right plot is a semblance time horizon, a section through line bin space. In both plots, the X represents the same pixel, where the trace intersects the time horizon. So far, so good. Now let's look at the left plot. This is the tilt azimuth section. It shows the semblance at the time of the X in the middle plot, and the line bin position of the X in the right plot for all tilts and azimuths. Adding in this subplot also changes the interpretations of the middle and right plots from the 3D case, because all of their pixels now correspond to the tilt azimuth coordinates of the X in the left plot. Again, the pixel marked X is the same in all 3 plots. Now looking at the actual data, we can see that the X lies on the side of a 5-dimensional semblance peak, which has well-defined boundaries in all 5 dimensions. So how do we know that this peak, and the other peaks we can see in the left and middle plots, actually correspond to real diffractions? Well, one way is by moving through line bin space. The left plot and the right plot both have axes that represent inline and crossline. If we move the X in the right plot towards the right, because of perspective effects, we should see the peaks in the left plot move the other way as we move past them in space. So let's try it out. I'm going to move the X in the right subplot 4 spaces to the right, 2 at a time. That's the positive inline direction. Watch the left subplot. There's 2 to the right, and there's 2 more to the right. See how everything in the left subplot shifted to the left? Let's back up to the beginning and do it again. There's 2 to the right, and there's 2 more to the right. Now we can do the same thing moving in the positive crossline direction, which is upwards in these diagrams. So again, watching the left subplot, that's 2 lines up, and that's another 2 lines up. You can see everything in the left plot shifted downwards, exactly what we'd expect from perspective effects. So one more time, there's 2 up, and there's 2 more up. So this suggests pretty strongly that these really do correspond to diffractions. The other thing is that if you do a little bit of depth conversion and figure out where these semblance maxima should be located in line bin time space, what you find out is that the largest amplitude ones correspond to the apices of hyperbolas that you can see in the conventionally stacked data. So how do we turn these semblance peaks into something that we'll be able to see on our output? We'll do that by using the watershed transform, which is a relatively new technique that has attracted some attention in image processing circles over the past few years. I'll show you how it works. Here's a 2D test function. I've marked the positions of all its local maxima with black dots. The objective here is to determine which hill each pixel in the image belongs to. Without getting into the details of how the watershed transform works, this is the result you get. The transform clusters together all the pixels that associate with any particular hilltop and gives them the same label. You can see where the term watershed transform came from. This thing was originally designed to work with local minima for the purpose of delineating rainfall catchment basins based on elevation data. The nice thing about the watershed transform is that it works on multi-dimensional data, not just 2D data. So we're going to run our 5-dimensional semblance information through it to sort out the spatial extent of each peak in 5 dimensions. Before we do that, though, let's take a look at the right subplot. You can sort of see that we shouldn't be too surprised if it were to turn out that all of those pixels belong to the same feature. The left and middle subplots, on the other hand, should show multiple features across tilt-azimuth space. And that's exactly what we get. So these, we hope, are the regions of that 5D semblance space that each correspond to a particular diffraction. Unfortunately, we run into a problem at this point. Some of you are probably wondering, why is he only using 8 lines by 10 bins? The answer is computer memory limitations. These 5D matrices are big, and 8 by 10 was the biggest our server could handle with 100 gigs of RAM. Now, Python is a bit of a memory hog. If I'd been able to do this in C, we probably could have done better. But the only multi-dimensional watershed transform that I could find was the Python one. So we had to fall back on the next best thing. Instead of doing a full 5D watershed transform, we ran separate 3D transforms at each bin, and this is the result. The good news is that quite a few of the feature boundaries on the left subplot haven't changed too much. Some of them are different, but not all. The bad news you can see on the right subplot. It looks like a Rubik's Cube now, and that's because each event has a different numerical label at each bin. We've lost all the information about lateral associations of events from bin to bin. Okay, so now we've got our watershed transform information. So how do we use that to get a result? Well, to show you that, I'll go back to this semblance diagram one more time. I mentioned earlier that the middle plot shows a semblance function through the position of the x in the left plot. Notice that I've marked a line in purple on the left subplot near the x. What we're going to do next is plot a diagram showing all the semblance functions through the points along that line next to each other. That gives us the upper left subplot of this slide. I've plotted the semblance functions as a fan, not as a grid, to emphasize that tilt-azimuth space is really a hemisphere, not a flat plane. The local semblance maxima are again marked with black dots, and for clarity we're only showing a limited time range around the time of the x from the last slide. Now, the upper right subplot shows the stacked data across the same range of coordinates. You can actually see here that different coherence peaks do correspond to distinct events that have different phases. The lower left subplot shows the watershed transform of the plot above it, along with the positions of the semblance maxima and the time extent of each feature through its maximum. Those are shown as black bars. That's how we build up our final result. We take the stacked traces from the upper right plot and retain only the amplitudes that lie at the positions of those black bars. That gives us subplot D in the lower right. These, we hope, are our diffraction signatures. That's how we make sure each diffraction only gets included once on the assembled trace in subplot E. We only select the trace that lies through the maxima. Now, as you've probably already realized, this is actually a 2D simplification because the horizontal axis is representing both tilt and azimuth space. In the real calculation, we don't use a 2D fan. We use a 3D cone that includes the whole time range and all of the search directions, so not all the maxima will occur in the same plane. Apart from that, though, it's the exact same reasoning. So getting to some results, this is line 101 of the conventional stack from our test data set. You can see that there are some clear diffractions starting around 900 milliseconds with indications of others at earlier times, but it really isn't easy to see them. Now, this is where we run into our second major problem, and it has to do with the reflections. It turns out that even when you use these huge circle gathers with folds of 10,000 traces and a geometry that favors diffractions, the reflections still don't get knocked down enough by destructive interference for the diffractions to really come through. Now, Berkovich's group apparently didn't have this problem, so maybe they know something that I don't. But anyways, what I found was that to get any kind of decent result, you had to knock down the reflection amplitudes artificially, and the only way we could do that was with FK filtering. Now that's really not what I wanted. It's obviously not good enough for production, but since it was our only option, we decided to go with it for proof of concept purposes. Now what I've shown here is what happens when you add FK filtering into the processing stream that produced the stack on the last slide. I'm showing this because it was obtained from conventional processing of the exact same input that we used to get our results, which I'll show on the next slide. So this is probably the best thing to compare our results to, this slide, rather than the last slide. So finally we get to see some output. The results are certainly encouraging. We can see quite a few diffraction hyperbolas now. Most of those weren't visible at all before. Now I have 5 lines here, so we can advance forwards and backwards a couple of times just so that you can see that they do move up and down just like you'd expect. Now if you take a closer look, you'll see that many of them have sort of a segmenty discontinuous appearance. Some of them are incomplete, and some of them seem to have trace-to-trace amplitude dropouts. I think that this is happening because we're using the 3D form of the watershed transform instead of the 5D transform. It turns out that there are so many semblance maxima at each bin in the assembly algorithm that you can't keep them all without cluttering the results. You have to come up with selection criteria to choose which ones to keep. Well, since the 3D form of the algorithm calculates each input trace independently of all the others, it's inevitable that some events will get selected for retention at one bin position and rejected at the bin next door. It makes it really difficult to tell which events are most important overall across all lines and bins. So this is a decent result. It shows potential, but it probably could have been improved a lot by better memory usage and a bit more RAM. I'll also show some time slices through that result, starting at around 400 milliseconds, which is where a number of events start to come in. Moving down to 440 milliseconds in 4 millisecond increments, you can see these open up into circles, just as you'd expect. I'll run back and forth a few times so that you can get a better look at this. Now, the event that I wanted to draw attention to is this one right around here. I hope that you can see that. If we look at how it develops over a few samples, particularly around 412 and 416, right about here, it almost looks as if the event has a phase reversal along this axis, just a little bit off the vertical. I'd love to believe that that might correlate with something physical like a pinch-out or such like, but I've got no way of knowing whether that could be the case. So we've had some success. The results are encouraging, but there are still several hurdles that need to be overcome, some of which I've already talked about. One of these is the memory limitations. I think that if we'd been able to use the 5D transform over a larger area, not necessarily the whole data space, but say 30 by 30, we likely would have had something better to show. The most serious problem is probably this business about the specular reflections not canceling out enough. Again, we had to use FK filtering on the input data to get anything resembling a decent result. That's fine for proof of concept, but not for production. This needs to be better. Another problem is that we sometimes see footprint artifacts, which manifest as phantom semblance maxima that tend to align with the line and bin directions in tilt-azimuth space. These things are a real nuisance. They have large semblance values, so the selection algorithm tends to grab onto them, but they're not real, and they can screw things up downstream. I haven't been able to figure out where they're coming from or how to get rid of them. Some acknowledgements. Steve Bennett helped out quite a lot with the early phases of the research, particularly with the I/O routines. Alex Wright dropped by on a number of occasions to take a look at intermediate results and make suggestions and so forth. I'd also like to thank the data holding company for allowing us to use their data, otherwise we wouldn't have any results to show. The StatCom staff, Daryl, Thomas, Jason, Jeff, and Doug for supporting me and Torr in this endeavor over the years. And this research was supported by a grant from IRAP.